Thank you for that introduction, Sonny. And since you've mentioned Micromen, I do have to explain, should you watch the movie, the storyline is roughly true. It's been amplified a bit to make it a better story. But Sam Phillips, who plays me, gets everything right except I didn't smoke, I didn't have a beard, I didn't wear a tie, and almost every detail is wrong. But it's still a good movie. So I'm here to sort of give you an overview of the topic area of artificial intelligence, machine learning, and I'm going to say a little bit about the work we're doing here in Manchester under the auspices of the Human Brain Project, which is the Spinnaker Machine. But first, let's go back to a bit of history. That didn't work. 65 years ago, in this rather inconspicuous house about 10 miles south of here, which is very close to where I live, about 1.5 miles from where I live, quite near the airport. There's this semi-detached house with the blue plaque over the brick gate, the brick archway that you see to the left of the picture. The light blue arrow is pointing you in the right direction. And this blue plaque announces that Alan Turing lived here, who was a founder of computer science and, of course, important in wartime code-breaking activities. Now, Turing came to Manchester because Manchester had the first operational machine that implemented his big theoretical idea from the 1930s of the universal computing machine. And Freddie Williams and Tom Kilburn were the first to actually switch on a machine that worked using this idea. And Turing came to Manchester to use that machine. While he was in Manchester, his interests were quite diverse. He spent quite a lot of his research time on an aspect of biology called morphogenesis, which describes how the cells differentiate. So we all start as a single cell, which divides into two identical cells, and then they divide, and so on. But at some point, symmetry has to be broken, because some of those cells will become brain cells, some will become skin cells, some will become gut cells, and so on. And Turing spent quite a lot of time on the mathematics of that symmetry-breaking process. But while he was in Manchester, he wrote at least one seminal paper on computing, and that's the one shown on this slide. And it's a paper with the evocative title, Computing, Machinery, and Intelligence. And it begins with the words, I propose to consider the question, can machines think? Remember, this was only 2 years after the first programmable computer ran its first program on June the 21st, 1948, and Turing is already wondering about how far these machines can go, in particular in emulating human intelligence. Now, in this paper, Turing decides that the question, can machines think, is not well posed as a research question, and so he turns it around into what he called the Imitation Game, and of course that's the title that Hollywood picked on for its recent movie about Turing. He called it the Imitation Game, but we simply know it as the Turing test for artificial intelligence. And he speculated that machines would advance over the second half of the 20th century, and by the end of the 20th century they would be capable of passing his test. He would be very surprised that even today, despite the phenomenal progress in the performance of computers, that no machine has convincingly passed his test. I say convincingly because there was some controversy about a run of his test at the Royal Society, I think last year, where a machine sort of appeared to almost pass his test, but most experts do not view it as a genuine passing of Turing's test. He would have been very surprised. And my take on this, my personal view, is that the reason that artificial intelligence, in the sense of imitating human levels of intelligence, has turned out much harder than Turing expected and many other people since Turing had expected, is that we've never really quite worked out what natural intelligence is. So we don't know how this thing inside each of our heads works as an information processing system. And since we don't know what natural intelligence is, it's very hard to build replicas of it in machines, in software or hardware. And that's why for the last 20 years or so, my personal research interest has has turned from just building conventional computers and making improvements in conventional computers towards using computer technology to see if we can accelerate our understanding of how the brain does its job. Now, there's quite a lot of activity in this area, and one area of artificial intelligence that has attracted a lot of attention over recent years is an area called deep learning. This is taking inspiration from the brain, constructing deep networks of neurons, but actually not following any kind of biological model, simply implementing large artificial networks that can perform impressive feats of machine learning. And these are now the state-of-the-art machine learning algorithm for a whole range of applications, and the big companies, Google, Facebook, and such like, are investing very large sums of money in developing deep networks. But these are not, in any sense, human-like intelligence. They are machines that do useful jobs. They can recognize and classify images. They're actually pretty good at language translation. So they perform a number of important engineered functions, but they don't really tell us much at all about how natural intelligence works, and nor can they replicate the more impressive capabilities of natural intelligence. Perhaps the pinnacle of the deep network achievements was, at least in the public eye, was the recent victory of DeepMind's Alphago system, which is a deep network-based learning system, which defeated the world Go champion in Korea. And now, those of you who've been around a bit will remember the great excitement in the late 90s when IBM's Deep Blue beat Garry Kasparov at chess, and this was considered a great step forward for artificial intelligence. But the critics said, chess isn't that hard, okay? Go is really hard. When you can show us a computer that can be good at Go, we'll be impressed. Well, it took about 20 years, so quite a long time, and some very powerful computer technology. But now machines can beat humans at Go, and Alphago has risen to the #1 Go player in the world rankings. It's a very impressive achievement. It has no idea what it's doing. It is not human-like intelligence at all. It's pure machine learning in its applied form. It's very impressive and potentially points to other uses, but it's not delivering on Turing's vision of human-like intelligence. We know that artificial intelligence has generated concerns, and we've heard warnings from some very senior figures. This particular headline was combining the views of Stephen Hawking, who, as far as I know, isn't a particular expert on artificial intelligence, but still has an opinion. Elon Musk, likewise, and Bill Gates, who arguably is a bit closer to the subject area, all warn about the existential threat of artificial intelligence. Now, this may be a concern in the long term, but my view is we're still a very long way from this really being a serious issue for humanity. We are decades away from it. Nothing is likely to form any kind of existential threat in my lifetime because we still don't understand the fundamental principles of natural intelligence. So all we can do with AI is build increasingly impressive learning machines. We can't build anything that would take over the sort of much more general and flexible human capabilities. Of course, at the more sinister end of the business, there is this announcement that the Pentagon is seeking $12 to $15 billion for AI weapons research. And I think there is genuine cause for concern about the prospect of autonomous weapons. There are large movements to try and get international treaties to ban the use of autonomous weapons. And partly this is because artificial intelligence isn't good enough to take the kind of sophisticated decisions that men are expected to take, or humans are expected to take in times of war. Of course, autonomous weapons aren't new. The anti-personnel mine, for which there is an international ban, is a form of autonomous weapon. It's a weapon that makes its own decisions about when it goes off. But what's really being talked about here are much more sophisticated systems. And as I say, I think a major argument for why an international ban would be a good thing is that the AI that can be used in these is really not going to be good enough to take equivalent decisions to humans. Now, here in Manchester, where in my group, we're not really an AI group, we're a bunch of engineers, and our contribution to this overall program has been to develop over the last 10 years the Spinnaker Machine. This is a brain-inspired computer at quite a large scale. Our goal from the outset has been to put 1 million mobile phone processors. These are processors designed by Arm Limited in Cambridge, to put 1 million of these into a single machine for brain modeling applications. So our goal here is not to apply AI to applications in the real world. Our goal here is to build a machine that's able to contribute to the scientific quest to understand the brain, to understand natural intelligence. And we now have 500,000 cores. That's 50% of the original target, and we are going to expand the machine to the full 1 million cores over the next few months. But our contract with the European Commission within the Human Brain Project was to make a platform available with 500,000 cores, and that came online at the end of March this year, and is one of several HBP platforms that are now openly available. So anybody here can join the HBP community and sign in and can run jobs on this machine over the internet. It is freely available. We don't charge for its use. You just have to join the HBP community to get access to it. And this is a machine which is capable of modeling simplified neural networks of the scale of a small rodent brain. 1 or 2 mouse brains, perhaps, is the scale of this machine. Sort of 500 million neurons if used optimally, with 500 billion synapses. So it's quite a large-scale computing resource, and people are using it. To date, the jobs that are being run are all typically quite small. But over the next year, we and others have plans to develop much larger networks to make full use of this machine resource. Now, a subsequent speaker is going to tell you, Karl-Heinz will tell you more about other HBP resources. What I think is interesting in the overall context of this work is the way that artificial systems are moving steadily into everyday life. So I guess everybody's heard about driverless cars. The picture here is the small Google driverless car, which has been let loose on the roads of California and appears to work quite well. I think they've had one crash into a human-driven bus. But overall, they're performing quite well in the familiar roads and the gentle climate of California. I have a car which is not fully automated, but has extensive driver assist. And I can tell you that in UK weather on the M6, it just gives up. Seeing through the windscreen, apparently, is something that humans can do, but computer vision systems are not yet quite capable of doing this. So as I say, in good weather on familiar roads, we can already build driverless systems. On bad weather, in strange terrains, this is much harder. But this is coming, okay? And there'll be significant societal impacts from the emergence of driverless vehicles over the next few decades. I think it's probably 2 or 3 decades before these become a practical everyday reality for most people. One of the societal impacts is that I understand in the UK about 10% of the entire workforce earns its living by driving vehicles. And so clearly driverless vehicles will have a significant impact on UK employment. And I think that pattern probably is similar around the developed world. Now, as we progress in our quest to understand more about how the brain works, that will feed into this technology. It will improve the capabilities of these machines. I think it'll still, well, we don't know how far we have to go before we get anywhere close to human-like intelligence, but I think it's a very long way. But even partial progress can enable us to build machines with more impressive cognitive capabilities. And there are examples of this in your smartphone. You can talk to your smartphone, and voice recognition is quite a sophisticated application of artificial intelligence. So these things are coming and will have increasing impact on our lives. And the other picture on here, by the way, if you don't recognize it, is Dyson's new robot vacuum cleaner, which I think it was launched in Japan a few months ago. It's quite an expensive robot vacuum cleaner, but it's unique amongst robot vacuum cleaners in that its motions are entirely based on a computer vision system. So it actually sees the room around it and navigates its way around the room using a vision system. So it's an impressive piece of technology. Whether it cleans the carpet, I have no idea. But I have a robot vacuum cleaner from a much earlier generation which wanders around the room in a fairly convincing fashion and completely fails to pick anything up. So it's good fun, but not terribly useful. So just to draw my part of this to a conclusion, I've presented a sort of a range of perspectives on this topic of brain-inspired computing. Turing's vision is still a long way off being realized, and he would be surprised that it's turned out much harder than he imagined. Computers are much faster than he ever imagined they needed to be, and yet they still can't pass his test. Artificial intelligence has been presented as an existential threat to humanity. My view is such words are rather alarmist relative to the current state of the art. I think we've got a long way to go before that becomes a serious concern. Deep networks, which kind of have their inspiration in our understanding of the brain, but are very abstracted from anything that a neuroscientist would tell you is actually there in the brain. They have, over the last decade, completely transformed the state of the art in machine learning, and they're now in everyday use. So when you talk to your smartphone, it is a deep network which is understanding what it is you've said. And deep networks also give us very good image recognition, image classification. Currently, they require very large machines to run on, so they're actually only within the reach of the very largest corporations who can afford big data centers with formidable amounts of computer power available. In the future, this technology is likely to be scaled down, and certainly the mobile phone manufacturers are desperate to find ways to build deep networks into the kind of chips you can put in smartphones. That's a big technical stretch, but there's a lot of interest in achieving that. And just as a final point, cognitive systems are here. They're getting more sophisticated. They're going to have a bigger and bigger impact on society looking forward. How rapid that is difficult to tell. My view is that again, driverless cars are, as a practical reality, are still 2 or 3 decades away. But there's no doubt they're coming, and a lot of research and investment is being put into that.